transitions display quantum criticality. As we discussed last time, this is the case in many polar materials, particularly ferroelectrics. And the question is, how is it that this can happen? Now, we know that metals near many different quantum critical points, spin density wave, antiferromagnetic, ferromagnetic, pneumatic, host novel, strongly correlated phases. What about metals near polar quantum critical points? Can we get interesting properties there? And I'd like to end with many more questions for future research. All right, please ask questions. And Frank, if you could look at the chat room, that would be great, because I can only handle so much at one time. Thank you. Okay. So, what is the interplay of quantum criticality with first order phase transitions? This is a question that our Murray Gang peers, Musio, Gill, and I have been thinking about for some time. There are many systems where we have classical first order transitions, and yet they display quantum criticality. Can we come up with a theoretical understanding of this? It certainly exists experimentally, but can we come up with some sort of theoretical idea? Well, classically, it's known that the strain energy density coupling is known to drive first order transitions in compressible systems. And so what we set out to do was to generalize this so-called Larkin-Pikin mechanism to the quantum case. What we find, and I just will show you the phase diagram, is if we look at temperature versus the quantum tuning parameter, for example, pressure, then we will have a first order transition ending in a quantum critical point. If we look at a field that's conjugate to the order parameter, for example, if it's polarization, this would be electric field, we know that classically we have a line of first order transitions that ends in two classical critical points, so we can connect the dots, and this is the sort of phase diagram we get. All right, elements of these ideas are summarized in this paper, and now we're working a little bit to extend those ideas. So let me start at talk about another scenario. You may think that naively, if a system is classically second order, then quantum mechanically it'll also be second order, and similarly the other way around. Well, some time ago, a group of people, which included Gil Onzarich, actually looked at quantum critical endpoints. In this situation, we have what we call the other scenario, namely at t equals 0, we have a first order transition, and as you come up, you get a tri-critical point, and then you get a second order transition. So in that case, you have temperature versus tuning parameter versus conjugate field, here B, and you end up with a second order transition, a classical tri-critical point, and then these ends to quantum critical endpoints. So what we're asking is, can we almost get the upside down version of this? Now, just to remind you, let's do a quick review of classical and quantum phase transitions, which we discussed in much more detail last time. So this is a nice phase diagram of lithium holmium fluoride and dipolarizing system. And of course, classically, thermal fluctuations melt the long range order, okay? And temperature is a tuning parameter. Quantum mechanically, here it's the transverse field, and there the tuning parameter is the field strength. And the important thing is, since the importance of quantum fluctuations is determined by the scale of the dominant frequency compared to temperature, we know that dynamics are important. And in particular, the effective dimension of the quantum system is the spatial dimension plus z, where z is the dynamical critical exponent associated with the dispersion. So omega goes like q to the z, okay? And since we know that, and what will the correlation length look like as a function of t coming down, Well, we know that omega goes like q to the z, and omega goes like t. So therefore, q goes as t to the 1 over z. We talked about that last time. So the correlation length will go as t to the minus 1 over z, right? So the key thing here is that the dimensionality is different at a quantum transition than at a classical transition. Here it's just the spatial dimensionality, and in the quantum transition, it will be d plus c. That will play a very important role in our argument. So let's actually go back to review the other scenario just briefly, okay? Here we start at a first order transition, and it's due to a negative quartic mode-mode coupling term in the effective action. As we turn on temperature, we get thermally induced order parameter fluctuations that drive that term from negative to positive. And that's how, and then we have an effective mode-mode coupling strength, and that's how we go from U tilde going less than 0 to U tilde going greater than 0. This has been seen in a number of antiferromagnetic and ferromagnetic metals. And in fact, there's a very nice review by Manuel Brando and collaborators in Review of Modern Physics, and this is one of the figures from that. So this has been seen in many, many systems. Now, what we're asking is the opposite. Can you have second order and then go up to first order? And that would seem to be difficult to do, to change it from positive to negative. But let's see how we can do this.
We have a question from Yashar Komijani.
Hi, Yashar. Sure.
Hi, Premi. Just a question. In this last diagrams, the last one is a 6-point function. So you're looking at the 6-point corrections to the 4-point function, right?
Yes. Yes. So what I'm doing is I'm getting order parameter fluctuations that are feeding into the mode-mode coupling term. Absolutely. Does that answer your question?
Yeah, just wanted to clarify.
Okay, thank you. So the point is that I get an effect, yes. All right, are there any other questions, please? All right.
So maybe can I ask you a follow-up question? So
sure. Could you speak a bit louder, please?
Yes. There is no 3-point or 5-point. Is there a symmetry that forbids those terms?
I was just giving a very simple explanation, but of course you could have, if you had a cubic term, it would always be first order. So I'm assuming that you just have even terms, and that could be by symmetry.
Okay, thank you.
All right, any other questions? All right, so I'll continue. So the motivation here, of course, not surprisingly, since we're talking about polar materials, is ferroelectrics, right? Now, at finite temperature and ambient pressure, ferroelectrics undergo, thanks to strong electromechanical coupling, undergo a first order transition where they develop a dipole moment, a polarization. So the poster child for perovskite ferroelectrics is barium titanate. Here it's a titanium that is displaced. Here is an old ferroelectrics have been studied for a long time. This is polarization versus temperature from Joni and Shiradi. They were actually studied quite a bit in the 60s with an aim to think about memory, but they were beaten out by magnetic bubble memories. But anyway, this is the polarization as a function of temperature. Then this is some work by Gabe Epley and Dennis McWan in 1985, where they looked at time-resolved X-ray diffraction, and they looked at T as a function of field, and you have a line of first-order transitions ending in a classical critical point. So the crucial thing here is that barium titanate is a classical first-order transition. Now, Dennis McWan also did some nice measurements where he showed that if you clamp the system, that is, if you don't allow any volume change, then actually the transition is second order. You have a diverging specific heat. However, if you unclamp the system, it becomes first order. And he used that to suggest that it's the coupling to the phonon that is crucial. So electromechanical coupling is crucial in the classical in making this first order. Now, last time we talked about strontium titanate, the isovalent cousin of barium titanate. It is stubborn. It doesn't want to be ferroelectric, but it can be nudged. And in fact, we talked about the fact that if you take strontium titanate and substitute oxygen 18 for oxygen 16, you can drive it ferroelectric. Here we have Tc squared versus oxygen 18 concentration. And the Cambridge group, led by Stephen Rowley, has shown that strontium titanate is just to the right of the quantum critical point, and you can include some oxygen. You can do an oxygen 18 substitution and drive it closer to the quantum critical point. This is actually a little bit to the left. Okay, so the question is, why is it that we have a first order classical transitions, but we seem to see quantum criticality? Now, one idea, which would be straightforward, is that all of these systems are just very close to their tri-critical points, and therefore applying pressure drives you into second order transition. Well, all of them being near tri-critical points, perhaps, but one of the questions that we set for ourselves is, can we come up with some sort of theoretical model which would give a description of this phenomenon? Just to show you why there's excitement about all of this, you notice that here, as I understand it from my experimental colleagues, the temperature range that you can get here, for example, 400 degrees, with just 6 gigapascals, that's amazing. Of course, that's because this is a compressible system. In other systems, like magnetic systems, I think you would have to have something, I understand you'd have to have a factor of 10 higher pressure to get the same kind of temperature range. So this is, in any case, this is our motivation for trying to understand this phenomenon. So let's go back to the Larkin-Pikin mechanism. This was a mechanism developed in 1969, where we had the interaction of strain with a fluctuating order parameter. Since electromechanical coupling is so important in ferroelectrics, we thought that we would revisit this old problem. So what Larkin and Pikin did was they had a strain, as we'll see, energy density coupling. They took a system, a compressible system, that had a divergence of the specific heat in a clamped system. So you clamp the system, that is, you have no volume change, and you have a well-defined second order transition with a diverging specific heat. Then you unclamp it. And when you unclamp it, you get a first order transition. Okay? So the Larkin-Pikin criteria for this first order transition is that kappa, which is the effective bulk modulus, is less than the specific heat over temperature times the square of the change in the transition temperature with strain. And here, let's just go through these terms. This is the kappa is the effective bulk modulus. This is the big K is the bare bulk modulus, and mu is the shear bulk modulus. And here I want to emphasize that shear is crucial. If shear is 0, like in a liquid, then we'll never satisfy this criteria. And this kappa, you might say, what is it physically? It's essentially the bare modulus times the ratio of the longitudinal over the transverse sound velocities squared. Okay? But shear strain is crucial. They emphasize that this is only in a solid. It's not in a liquid. And you see the appeal of this because we know in barium titanate, when it's clamped, it has a diverging specific heat. And we know that it's first order the unclamped system. So what Larkin and Pikin did was they said coupling of the uniform strain to the energy density leads to a macroscopic instability of the critical point, which leads to a first order transition. And so the natural question we asked ourselves was, can we generalize this to the quantum case? So in order to generalize it, we're going to have to study the classical Larkin-Pikin mechanism a little bit because we're going to have to reformulate it in such a way that we can generalize it to the quantum case. So they considered the absolute simplest case an isotropic elasticity and a scalar order parameter. So they were considering a compressible system where the order parameter is coupled to the volumetric strain. So we're going to write down the action, and it's going to have three parts, A, B, and I. Now, here I've written the action in such a form with the Lagrangian density, partly in anticipating the generalization to the quantum case that, of course, classically, here were temperature, classically, this is just the Hamiltonian density. Okay, so let's define these terms. The Lagrangian term sub A is just the physics of the order parameter. In the simplest case, it's a 5-4 theory. A is the tuning parameter proportional to temperature, and B is the quartic coefficient, right? So here, because we have a second order transition, B is greater than 0, A is of course proportional to the reduced temperature, and in the clamped system, this is the sole contribution, okay? So then we have a very nice second order transition, okay? So this is the physics of the order parameter. Now, what's B? B is a function of the local atomic displacement, and it's going to describe the elastic degrees of freedom. Here, sigma is the external stress, U of A is the local atomic displacement, EAB is the strain tensor, and ELL is the volumetric strain. So this term here describes the elastic degrees of freedom. Now we have this Larkin-Pikin interaction. This is the interaction between the volumetric strain and the squared amplitude of the order parameter. And alpha is the coupling constant associated with the strain dependence of TC. Now, we can think of psi squared as the energy density of the order parameter. So in this sense, this is a strain energy density. So this is what we have. We have an action where we have physics of the order parameter, elastic degrees of freedom, and strain energy coupling, density coupling. Okay, now the key idea is to integrate the Gaussian elastic degrees of freedom. So we start with a partition function like this, we integrate out the elastic degrees of freedom, and we get an effective action. And here, believe it or not, there's a difference between curly S and the effective action. I don't know if it comes across. This is the effective action, which is just a function of the order parameter. That's what we're after. Now you might say, wait a minute, what's so difficult about this? I remember how to do Gaussian integrals. Well, we have to do this with some care. And this is emphasized in the Larkin-Pikin treatment.
I mean,
right?
there's a question.
Of course.
Navinder Singh.
Yes.
Yeah, Professor Chandra, so I have a question regarding, so the three terms actually, so is there a boundary term also for the clamped and
a very prescient question. We're going to put in a boundary term when we define the strain. So you're ahead of me, but you're completely correct. Yeah. There's going to be a boundary term. And that's the big difference, as you've already anticipated, between a liquid and a solid. Well, of course, there's a shear modulus, it's a big difference, but we'll be talking about that shortly. You're ahead of me. Okay, so hopefully I'll explain that in a slide or two, but please ask again if I haven't been clear enough. Any other questions? Okay, so just as Navinder was asking, we have to be very careful about the elastic degrees of freedom. Okay, in a solid, we have normal modes where the wavelength is much, much less than the system size. Those are like sound modes. But what about the boundary modes? What happens when the wavelength is comparable to the system size? And what we'll find is the Larkin-Pikin effect is like an elastic anomaly. We're going to integrate over these boundary modes, and they're going to generate a non-local order parameter interaction in the bulk action. It'll destroy the locality of the original theory, and paradoxically, they're going to be independent of the detailed boundary conditions as a bulk term in the action. So let's see how this all works. In a system with periodic boundary conditions, and that was the Larkin-Pikin choice, they're going to write the strain energy the strain tensor as a Q equals 0 term, which is the boundary term, and then finite Q terms, which are the fluctuations, fluctuating atomic displacements, okay? Now, one way of thinking about this is that at finite Q, we're only interested in the longitudinal modes, but at Q equals 0, there's no distinction between longitudinal and transverse, okay? Now, here V is, of course, the length squared. U is the Fourier transform of the displacement, and the Q vector here is going to be 2 pi over L times integers. So we're going to be dividing up the strain into these two terms. Okay. Now, interestingly enough, we are formally making our solid into a 3 torus, and these boundary modes, what we can think of is that the integral over the Q equals 0 strain around a torus is going to define the number of line defects enclosed, a sort of flux. And here we can think of BA as the Burger's vectors of the enclosed defects. So the boundary modes of the strain have a topological character. So now let's integrate over the strain fields. The correction to the action of the order parameter, if we are interested in the effective action as a function of the order parameter, we can think of this as the action of the original action of the system with clamped plus these other terms, where e to the minus s is going to be this integral. Where here we're going to be integrating out all the terms in the action that have anything to do with the displacement. Right. So this is what we get when we do all that. The resulting action. The resulting action will be S of A, the local term here, but with a renormalized short range interaction. Okay? And then we're going to have this other term. Now, let's look at this other term. Notice a couple of things. First of all, it's a distant independent interaction between energy densities of the order parameter. It's highly non-local. This term is all local. This is highly non-local. So it's distant independent interaction between the energy densities, and it's this term that drives a non-perturbative first order transition at arbitrarily small couplings. Now, it is true that we have a perturbative term of order lambda squared that leads to a renormalization of the short range interactions, okay? But since the Larkin-Pikin effect is for arbitrarily small lambda, this is not that important. And in what proceeds, I'm not going to distinguish between B and B tilde, B star. Okay, now let's look at this term. This is the effective bulk modulus that we talked about before in the Larkin-Pikin criteria, and it comes from two terms. The Q, when we integrate over the Q equals 0 term strain, and that's how we get this K is the bulk Baire modulus. We get this attractive term, okay? And this is only present for the clamped system. We do not have that Q equals 0 term for the unclamped system, okay? Excuse me, it's only present for the unclamped system. We do not, this should say it's only present for the unclamped system. Sorry about that. Okay. Yeah. Now comes this term.
I just saw in the chat that there are some questions
sure.
related to some clarification. I don't know if they're still up to date. Yasha, John,
sure.
do you want to? You still have a question?
I guess I was just wanted to make sure that mu is connected to the shear.
Yes, mu is the shear modulus. I'm about to talk about that.
Oh, I see. Okay, you got the answer in the chat. No,
yeah.
I understand.
Okay.
Okay.
So
thanks.
let me go through this again because I made a mistake on the slide. Sorry about this. The Q equals 0 strain is only present for the unclamped system. This has to be changed, okay? This is only present for the unclamped system. And this is an attractive interaction. What's more subtle is this term. This is a repulsive term. And it's subtly from integrating over the finite Q elastic fluctuations, okay? When we do this integration, that's where we get this B star, the renormalization of the local term. However, to get a local term, we have to sum over all Q. And remember that the finite, that we had that term excluded explicitly Q equals 0 fluctuations. So this is a residual repulsion due to the boson hole in the longitudinal interactions. It's present for the clamp system. And that's consistent with the fact that in the clamp system, we have a second order transition. So what we have to check is that this term, which is attractive, and this term that is repulsive, that the attraction wins. And once again, and this was asked by Yashar, this mu is the shear modulus, and the prefactor is only non-zero for finite shear modulus. So solids, but not liquids. So the shear modulus plays a very important role here. Sorry about this typo, that should be unclamped. So, so hopefully, yes. So again, this is a non-local distant independent term. The prefactor goes as 1 over kappa. It has two terms, an attractive term and a repulsion term that comes from doing the integration, and but only because this is right. All right. So what's the resulting action then? The resulting action looks like this, and what we notice is that this is the volume average of the energy density. This term is related to that. And this is an intensive variable. Now, first of all, since it's a volume average of the energy density, we can actually rewrite the action in this very simple way. But then we notice that this is an intensive variable, and therefore the fluctuations around the thermal average vanish in the thermodynamic limit. So we can write this, and therefore we can write our action as a set of self-consistent equations. Let's go back, that maybe went too fast. What we can do is we can input this here, and therefore we can write our action. We have a set of self-consistent equations where we have 1 over T times this. Here, this is from, here we have, we've used this energy, this volume average of the energy density, and we're defining this again in terms of the action of the clamped system. Okay, so now we have to solve this. Now there are many ways of doing this. The simplest is to introduce an auxiliary strain variable. Then we can define this free energy, and our action will look like this. Okay, so we'll have our Lagrangian in terms of the order parameter. A is the tuning parameter. Now we have a lambda phi size squared, and then we have this kappa volume over 2 times phi squared. Okay, and in order to impose self-consistency, we look at the stationarity of the free energy, and so we have self-consistency. So that's where we are now. Now we have two possibilities. The first is to integrate out the order parameter fluctuations. Okay, we can integrate out the psi, and then we should get a renormalized bulk modulus. It's our effective bulk modulus minus a correction. And it turns out that if you do that, you find that this correction actually is proportional to the energy fluctuations. And if they diverge, as they do in d equals 3, then you will always have a macroscopic instability. This will go negative. You'll have a macroscopic instability, and you'll always get a first order transition. Okay. So that's one way of doing it. Another way of doing it, which is what Larkin and Pikin did, was you can integrate out this elasticity variable. Okay. So that's, it turns out that both approaches thankfully give the same thing, but in the interest of time, I'm just going to talk about the Larkin-Pikin, the approach, and we can integrate that out. The reason I'm going through this carefully is we'll see how it can be generalized to the quantum case here. Now, Larkin and Pikin noticed that this term can be absorbed in this Lagrangian density if we shift the tuning parameter by 2 lambda times 5. So that's exactly what they did. They said, let's shift that tuning parameter to a plus 2 lambda phi. Okay, so they're going to call that x. Oh, sorry, there's an x here. Well, anyway, this x is a plus 2 lambda phi. And now let's define the free energy of the clamped system. The free energy of the clamped system is just this, where this is the action associated with the clamped system. Now, the free energy of the unclamped system, F tilde, will be F of x, where x is a plus 2 lambda phi, plus this kV over 2 times phi squared. So we have a shifting of the tuning parameter due to the energy fluctuation. Now, notice that we have a phi squared here and a phi here. So what they then said is, look, we can take, if we take the f dx, remember x is the tuning parameter, and we take 1 over volume, we should just get the volume average order parameter fluctuations. So let's redefine phi in terms of that. Well, if we do that, then we can redefine phi in terms of f, which is the free energy of the clamped system, and we can redefine phi in this way. If we rescale our variables, the two equations describing the unclamped system, this is f as a function of a actually, where f of x and plus lambda, and the second, and the square of the derivative of f of x with respect to x. And of course, a is x plus this. And then here we're just putting in this, this term for phi. And these two equations have to be solved self-consistently. And of course, a is proportional to the temperature, is the tuning. So let's see how this works for Larkin-Pikin. The continuous transition in a clamped system. So we have f, remember f is the free energy of the clamped system, goes as minus 2 to the minus t to the 2 minus alpha. If we work it out, we see that there is a non-monotonic relationship between t and x. So we have t, we have x, we have a non-monotonic relation. If we then work out what the free energy is to the unclamped system, and here what we're doing is we're mapping out the free energy minimum, we see that we have a first order transition for the unclamped system. Okay? So the point is that this non-monotonic behavior between t and x is what gives us the first order transition. Okay? And again, we're tracking the minimum. Now, how would we extend it to the quantum case? Strictly speaking, we have to go back to the strain field, the definition for the strain, and we need to include frequency dependence, okay? And it turns out when we do that, we get non-local terms, not just in space, but in time. But then you can actually show, and we don't have, this is, I'm just giving you a flavor for this, we don't have enough time to do this, but what you can show is that these non-local terms don't have the same scaling dimension as the locally repulsive terms, so they don't actually change anything. So the simplest way to show you what happens in the quantum case is to say, we know that in a quantum case, it's like adding more dimensions. So we know that for D greater than 4, 4 is the upper critical dimension. Remember, the upper critical dimension means that the interactions are irrelevant above 4, okay? The quantum, in the quantum case, D is D space plus C, for ferroelectric D is 1, but we'll talk about that in a minute. But let's look at the case for D greater than 4. Well, in that case, we have alpha is equal to 0. So notice that if we go through the same Larkin-Pikin argument, then we find that there's a monotonic relationship between T and X, suggesting that we have a continuous transition, okay? Now, of course, as I mentioned, this assumes you have the same action as before, which, as it turns out, you do, but you have to show that, okay? But I'm not going to take you through that right now. Now let's look at the marginal case. This is important for ferroelectrics because we have 3 plus 1. In the marginal case, the singular part of the free energy, this is a logarithmic term, we have a very weakly non-monotonic relationship between T and X. At T equals 0, we have the difference between the two free energy relations is exponentially small, and therefore we have a very, very weak first order transition. And that would suggest that we should see logs. To my knowledge, those have never been seen experimentally. So that's what's sort of driving us to say that, look, if we take the Larkin-Pikin system and look at the quantum case where the dimensionality is increased, then in fact we have the possibility of a continuous transition. Okay, so I want to also give you a flavor for the other project. So let me just tell you a little, summarize our results. We got this phase diagram. We have quantum criticality here. We know that there are 2 classical critical points. We can connect the dots. There are a number of experimental signatures that one can develop. The main thing here is the fact that it's a simple model which shows that just because a system is classically has one type of phase transition doesn't mean that quantum mechanically it has the same. One of the very nice things about this possibility is that we have new lattice sensitive settings for exploration of exotic quantum critical phases, which are particularly important if we want to establish any kind of universality. Of course, we have more questions than answers in all of this. In real systems, we of course have elastic anisotropy, domain dynamics, what happens with disorder. And last but not least, to sort of segue into the next topic, how can we generalize this to metallic systems? We know, for example, in the case of chromium, which has a spin density wave, that you have first order transitions, but Gabe Epley and collaborators have seen quantum criticality in chromium. So we know also that in systems like what Chimiao told us about iron pnictide systems, there are cases where you seem to have classical first order transitions ending in quantum criticality. In the enigmatic system uranium, ruthenium 2, silicon 2, that may also be the case. So is there a way of generalizing this kind of argument to treat other systems? And that's something, of course, for the future. But speaking about metallic systems—
We have a question by Elio.
Oh, sure. Yeah, hi, Elio.
Hi, Premi. I have a question actually for this, I think, crucial part of the story, which is the effect of these boundary modes in the non-local interaction. So I was trying to understand actually what are the conditions for this to happen, and somewhat relatedly is what determines coupling and actually even the coupling between the elastic modes and the order parameter, or what is actually even the subdivision between order parameter and elastic mode, since everything is atoms.
So this is a result of having this strain energy density interaction. Okay, I didn't quite understand your question, so you have to go back. So it's a result of having this particular kind of interaction.
Right, so the question is maybe more, so what determines, or how do you know that this is the right coupling, or what is even the subdivision into these various parts? How is that motivated?
Okay, so all I'm, at the moment, all I'm doing is revisiting the original Larkin-Pikin argument.
Right.
So the original Larkin-Pikin argument was, if we have this coupling, we can show that in 3D there will always be a first order transition. So our motivation was, this is a case where we know there's always a classical first order transition. What happens to it quantum mechanically? But
Yeah,
if your question is whether this is actually relevant to the physical systems, this
Yes.
is highly simplified. For example, in the real physical systems, we have anisotropy, we have all kinds of other things which have not been included in this. But our idea was to take a simple model where we know there's always a first order transition and to see whether quantum mechanically we can get anything different. But in terms of making direct contact with the materials, we have to do much more work. This is just the beginning. Does that address your question?
Yeah, I think I followed the math. It was just
Yeah, so all that I'm doing is I'm at the moment, I'm just revisiting the classical Larkin-Pikin mechanism, filling in some of the gaps because it's a little bit telegraphic, and filling in some of the gaps so that we can generalize it to the quantum case.
Okay, thank you.
Okay, and actually, let me let me get to the end of this. But you're completely right that there are many aspects of the real system that may be different in this. That's why I mentioned about domain dynamics, about elasticity. You might have a multi-component order parameter. There are all kinds of things that could be different. But our point was, let's take this simple model where we know there's a first order transition and see whether it can actually be continuous. Before I switch gears, are there any other questions about this?
Yes, can I ask one, please?
Oh, of course.
So just looking at this picture, the point is that this first order transition ends in a second order quantum critical point, which is of course theoretically very interesting. But experimentally, you never actually go to t equals 0. So what would be the signatures of this at finite temperature?
Yes, so that's actually very important. And we've been talking about dielectric loss and hysteresis. And I should say that we're still having some discussion among ourselves about whether this is actually a quantum critical point or a quantum tricritical point. And so in some sense, how the free energy comes down to zero temperature will be very important in determining those experimental signatures. But yes, as you point out, the experimental signatures are crucial. There's also, of course, the Grundheisen parameter, the ratio of the thermal expansion on the specific heat. And that would be a nice way, since we know that it will, if this is first order, will change sign across here if G is pressure. But and diverge here, but if it's just first order, we won't get a divergence. So Grundheisen is crucial here. But we're still working that out. What the Larkin-Pikin does not give us is how the free energy of the unclamped system varies with order parameter, and that's what we're just in the process of working out. And so the results of that, and whether it's tricritical or just a regular critical point, are something that will determine this a little bit more.
Okay.
So that's work in progress. Are there any other questions? All right, then I'll move to this second topic. And here, and this was an effort led by Pavel Volkov, who's here at Rutgers. And here the motivating question was could we find novel, strongly correlated phases in quantum critical polar metals? And I won't do justice to all of Pavel's hard work because I've been told that I have to keep to time, so which is fine. I want to give you a flavor of all this, but this work has just recently been published, and I point you in that direction if there are questions that I'm not able to address, but of course I'm happy to take them also. Okay, so let's unpack the title. We said it was Multiband Quantum Criticality of Polar Metals. That's a mouthful. Okay, what's a polar metal? Okay, I think that question was asked actually last time. Is it possible to have a ferroelectric metal? Well, let's just talk about it. We talked about strontium titanate being a somewhat stubborn cousin of the poster child barium titanate, though it's coming into its own these days. If you just nudge it, for example, with calcium, you can make it go ferroelectric. And this is, I'm going to take some graphics from this nice article by Cameron Banya's group. If the blues here are titanium, the little balls here are oxygen, and strontium, which would usually sit here. If you replace the strontium by a calcium, calcium's much smaller, it can rattle around, and you can get a ferroelectric. And here it's important to emphasize that the critical boson is transverse optical phonon with Q of order 0. I should say, last time we talked about dipolar interactions. Well, we'll talk about them later, but they're going to be important for giving you a gap between the transverse and the longitudinal optical. Okay, so this is a ferroelectric. But similarly, we also talked about the fact that if you take strontium titanate and deplete it, take away this oxygen, it can go metallic and eventually superconducting. And we talked about some of the challenges there. So what happens if you do both? What happens if you dope a ferroelectric, okay? So when you dope a ferroelectric, first of all, you're going to get screening of the dipole moments, so no polarization. However, the inversion symmetry-breaking transition remains, and this was actually pointed out early on in the work by Anderson and Blount. So that's exactly what Banya's group did. They took strontium titanate and they added calcium, okay, to give it that critical polar mode, and then they depleted the oxygen. So here we have a polar metal, okay? And what we see here with these arrows are the transitions. This is resistivity. The transitions, if it had not been screened, these would have been ferroelectric transitions. These are structural transitions from nonpolar to polar states, okay? And just for the record, I'll just say that you notice that this also goes superconducting. That's a whole other issue. We won't be talking about that today, but that's a very interesting other issue. Okay, so it turns out that intrinsic, there's a lithium, osmium oxide system, and engineered, like doped ferroelectric polar metal do exist. And indeed, in the search for vial semimetals, a number of polar semimetals have been found. One can do chemical tuning of TC, okay, a little bit like in strontium titanate, chemical tuning of TC. We can bring TC down. We, of course, I'm talking about the collective. I'm too impractical to be in the lab. And so then the question is, in these systems, could we actually get novel metallic quantum criticality? Now, there's a big challenge here. How do we get strong electronic coupling to the critical polar mode? Also, we have Coulomb interactions. Now, in the weak screening limit, they lead to a splitting of the longitudinal optical and the transverse optical mode. So when we're interested in quantum fluctuations, we're only really usually interested in transverse optical quantum fluctuations because of this gap. So how do we go about doing this? Well, it turns out that the usual couplings that we have are irrelevant in a scaling sense near the quantum critical point. And we want to get strong coupling. So one idea is to look at Yukawa coupling. Yukawa coupling is a coupling of the order parameter to the electrons, and it's known to produce strong correlations for lots of other quantum critical points. But here we have a bit of a challenge because our critical polar boson breaks inversion symmetry. What do we do for a polar quantum critical point? So how do we manage a Yukawa coupling to the polar mode? In other words, how do the electrons couple to an inversion breaking, symmetry breaking field? And here, for example, T versus some tuning parameter, pressure, doping, strain. Here we have a symmetric phase. Here we have inversion symmetry breaking, and we're asking, can something interesting happen here? what we want is a fermionic bilinear that breaks inversion symmetry, but not time reversal symmetry. We're saying not time reversal symmetry because most of the materials of interest don't have large spin orbit coupling. Okay? So that's what we want. So let's take a coupling like this, where here's our critical polar boson, and this is our fermionic operator. Suppose we have our fermionic bilinear. Suppose we have a single conduction band without spin orbit coupling. Well, in that case, we don't have much choice. Our fermionic bilinear has to take this form, and for inversion and time reversal symmetry, both, we need this F0 to be even in K. So it is not possible to break inversion symmetry breaking without time reversal symmetry breaking. So if we want a Yukawa coupling to the polar mode in a single conduction band, we need spin orbit coupling. Okay. All right. It turns out that the Yukawa coupling to the polar mode can be done if we allow in multibands. And there are a couple of polar metals that are multiband. Here, the polar mode couples to an interband bilinear, and no spin orbit coupling is required. If we think of the parity operator in two bands, time reversal is like complex conjugation. Parity operator, if we're operating on band space, here we have different bands, and here we have same bands. We're interested in interband bilinears, and here this will be even, this will be odd, and let me just give you a physical picture of how this can happen. A physical picture is something like this. Let's assume that the bands arise, again, we're going after flavor. Let's assume that the bands arise from two distinct orbitals, let's say S and P. Here we have different parity, here we have same parity. These two cases are where we have the symmetric, okay, and here we've broken inversion symmetry. Let's first look at different parity. When we have different parity, then when we have inversion symmetry breaking, we can mix linearly. We can have linear mixing by the inversion symmetry breaking perturbation. And so we have a non-zero hybridization between the bands, which is not allowed here. Okay, so now we have a non-zero hybridization. If we have the same parity, okay, then we have to, momentum dependence is necessary. We can't view this locally. However, inversion symmetry breaking means that interband hopping to the left is going to be different than interband hopping to the right, a little bit like dimerization in the Sushri-Verheer model. And in both cases, the interorbital hopping changes with the inversion symmetry breaking. So that's a sort of simple cartoon of how this can work. Okay, so in order to drive novel metallic behavior, we're going to need gapless particle Hill excitations. In other words, we're going to need band crossings close to the Fermi level. Okay? And this can be realized by doping or by doping, all kinds of things, but we're going to need a band crossing. Okay, so what one can do is look in three generic cases. Okay, so we can look at 3D nodal lines, 2D nodal points, and just for completeness, we also considered 3D wild points, which are driven, of course, by broken time reversal symmetry. Here we found that we had Fermi liquid, here we had a non-Fermi liquid, and in this case, a marginal Fermi liquid. I should say we did this both with and without Coulomb interactions. Without Coulomb interactions would be relevant, for example, in an elemental case, or if you had Fermi pockets nearby that would lead to strong screening. We also looked at Coulomb interactions, and they led to tremendous anisotropies here, and they gapped the longitudinal modes. So in order to be on time, so that we have time questions. Let me just summarize again. Hopefully this is a taster. Can we get novel phases in quantum critical polar metals? The answer is yes. If we have nodal multiband metals near polar quantum critical points, these will act as promising settings for very interesting behavior. We also thought about experimental signatures, specific thermodynamic, transport. In each case, the critical polar mode is strongly renormalized. You get unusual dispersions, and there are a number of interesting points that crop up. Again, this is in this paper. And the good news is there are already a number of polar metals with multiband structure. For example, tungsten ditelluride, molybdenum ditelluride, lithium osmium oxide, and many more that are predicted. So we're hoping that this will be a new setting to look for novel electronic phases. All right. Let me, as always, this is not the end, but the beginning in a different sense. Let me give you a brief summary and give you many open questions, and hopefully this will give you a chance to ask me some more. I've tried to give you a flavor for two current research projects. One is for insulating polar materials, namely how is it that we can get a first order classical transition and second order quantum criticality. Then the question is, can you get strongly correlated phases in metals close to a polar quantum critical point? Our answer is yes, but you need to have nodal multi-band structures. But of course, there are many, many questions going to ask. Since we're just talking about polar metals or metallic systems, there are questions about transport. Last time we talked about doped ferroelectric and doped strontium titanate. What's the T-dependent transport? There are also issues about the temperature dependence in the polar metals. Then there's a big question about superconductivity. We saw that the polar metal that Benye and his group studied went superconducting, also strontium titanate, electron doped strontium titanate. There are many, many issues about the superconductivity mechanism. We can add spin also, multiferro quantum criticality. To my knowledge, there's only really one or two experiments on this. There've been some nice predictions from Nicola Spalding and Sasha Belatsky about taking strontium titanate, turning it ferroelectric with adding barium, and then making it multiferroic with europium, and they have specific predictions for that. And the list goes on and on. So I hope it gives you a taste for this area, and please join us in the adventures. Thank you very much.
Okay, let's thank you, Premi. Yeah, we have time for questions.
I think did I answer all the questions? I doubt it.
So I have there is a question in the chat, in the participant list. So we have a question by Daniel Munoz Segovia.
Okay, sure.
Yeah, hello, can you hear me?
Yes, hi. Okay,
thank you for that very nice talk. It was very interesting. And I wanted to ask you whether you can comment more on the Fermi liquid behavior you have found in online semimetals, because as far as I understood, they are quite similar to massless two-dimensional Dirac fermions in the band structure and topologically. So what is can you comment more on this difference between Fermi liquid and non-Fermi liquid?
Yeah, so actually this is a very, thank you for the question. And of course, I didn't get much time to tell you about it. This is a very strange Fermi liquid because the system has, for example, the critical boson has a sound velocity that's closer to the Fermi velocity than so the point is that it has anisotropy and it has some very strange dispersive behaviors, but it doesn't have the instabilities that these other two do. That's what we found. And we made some predictions for experiment based on some of those anisotropies. So there's very strong, in each case, there's very strong renormalization of the critical boson. So when I say Fermi liquid, that doesn't mean it's not interesting. It's just not non-Fermi liquid, but there's some very interesting properties to this. Thank you, Daniel.
Okay.
So then there is a question from Yasha Komijani.
Sure.
Hi, Premi.
Sure.
For your talk.
Hi.
I have a rather embarrassing question. Can you say again?
There are no embarrassing questions, but I can't hear you.
Sorry, let me see. So can you say again, what is the difference
Okay,
between clamped
so
and
in the,
unclamped,
okay, we're back
device?
to the first topic. In the clamped system, there's no coupling to the, okay, so let's
like
go back.
experimentally, what is the difference? Like,
Oh, experimentally, you're not allowing the volume to change. So you clamp it, the volume cannot change.
I see.
And when you unclamp it, the volume can change.
But the volume cannot change in the clamped direction, but in the unclamped direction.
No, it's hydrostatic pressure.
Everywhere.
Yeah,
I see.
that's what was done with
Theoretically,
a tightening.
what is the difference
Pardon?
theoretically? What is the theoretical difference on the boundary conditions?
Oh, well, that's be there. Okay, all you would have were the fluctuating atomic displacements. You would not have this boundary mode. This is Q equals 0. You would not have that. Okay, so, and again, when we go through this, here, we would have this term. This comes from integrating over the finite Q elastic degrees of freedom. We would not have this term. So as a result, there would always be a second order transition because here we have a repulsive interaction. This is repulsive. There's no attractive term.
Right,
So
right.
the point is that the key point is that this term, this boundary mode term, would not be present. So
right.
Another way of in the clamped system, the point is that you have the volume doesn't change and you do not have this boundary mode. When you unclamp it, then this boundary mode is important. And
yes. And the body.
Pardon?
Sorry.
And in barium titanate, they actually see this. Where not, I mean, when they clamp it, it's second order. When they unclamp it, it's first order. And it's hydrostatic, not uniaxial. Maybe sorry if I wasn't clear on that.
No,
Does that?
Maybe a follow-up question, sorry, on this interaction that you drive, non-local interaction. So within the mean field, this just renormalizes the mass, right?
Which, this one?
No, this non-local interaction, as if I understand it, within the mean field theory, it just normalizes the mass, right?
Well, it's more than that.
Shifting.
Because remember what Larkin and what Pikin did is, you're right that it renormalizes the mass, but we have, I mean, it normalizes the mass, but we have this other term here still. And so
yes.
As a result, we have, let's go back to this, our equations are not just renormalizing the mass, that would just be this.
Right.
We have another term here, and that's what leads to this non-monoticity.
I see.
You see, because it's thanks to this term. So for example, when we, so it's because of that term that you get these two branches. And that's what makes it go first order. Does that clarify?
Yes, yes, thank you.
Okay, thank you.
Hilbert has a question.
Sure.
Hi,
Hilbert.
Nice talk, Prema. I have a question concerning the the role of the electrons in your treatment. If you go back to
in which project,
Miller's
please?
theory, if you go back to what do you mean? No, in general, the quantum magnetic quantum phase transitions, as treated
Yes.
by Hertz and Miller's, for instance. The problem arises that if you look at this as completely a bosonic theory, you also have, you neglect the dynamics of the conduction electrons. So that introduces another temperature or energy scale in the system, or frequency scale. And my question is, and that leads, for instance, to the problems that you have with the Kondo effect, or some people could talk about Kondo breakdown and so forth. So the question is, what happens to the conduction electron dynamics in your system? Is that treated as well in your approach?
Well, in the first approach, we're treating insulators, so we don't have any. Okay, in the metal approach, we're interested in the electrons interacting with this critical boson, and we're looking at the effect that the bosons have on the electrons and the effect that the electrons have on the bosons. And we actually looked now at, what we've done is we looked at the stability of what we looked at was, we used actually the Hertz-Miller's treatment to come up with whether or not we had Fermi liquid or non-Fermi liquid behavior. But I don't quite understand what your question is.
The question is, if you, can you hear me?
Yes.
The question is, when you look at the Hertz-Miller's treatment, they're actually looking at simply the, as I call it, the electrons being spectators and not being taking part in the dynamics, and that is not this is something that is leads to the problem of having additional energy scales, and there are various approaches to solve this problem. One would be the model by Ximiao C, and then there's also the model by Peter Wölfle and Abrahams on the critical quasiparticles to actually get a coherent picture of the quantum phase transitions, including the dynamics of the electrons. And the question is whether that is necessary in your case, and I gather from your answer to my previous question that actually you have treated the interaction between the polar modes and the electrons at full footing.
That's what we've tried to do, yes.
Okay, thank you.
Thanks.
Okay, we have another question in the participants list from Victor.
Hi, Victor. Sure.
Hi, Premi. Just a simple question about quantum criticality.
Sure.
You had this equation about the effective dimension, df equals the dimension plus z.
Yeah.
Is there a restriction that my effective dimension needs to be an integer, like in normal dimensions, or like for the z, or can z be anything?
Z can be, we can have weird critical, you can have weird anomalous z's. So at this point, we're just saying that's the effective dimension.
Oh, okay. So I could have an effective dimension of, I don't know, 9/4.
We don't tend to see that so much, but we have weird theories.
Okay. All right. Thank you.
Okay, then the next question is from Navinder Singh.
Okay. Hi, Navinder.
Yes, hello. My question is related to Sam's question regarding the experimental signature of quantum critical point. So, for example, in cuprates at the quantum critical point, putative quantum critical point, the heat capacity is proportional to minus T log T.
Yes.
So whether such kind of the thermodynamical signature is expected when you have fluctuating polar movement around the quantum critical point, because zero temperature is never reached in experiments. So what kind of experimental signature one would like to expect from this scenario? Yeah.
Well, for example, if we really believe that it's first order all the way down, it would be very interesting to look at dielectric loss or hysteresis, and in principle, it should start to go away. Also, again, the Grunheisen ratio would be very good, which Hilbert, of course, knows a lot about, the thermal expansion over the specific heat, because that would also tell you, be able to distinguish between whether or not this is first order or whether or not it's a it's second order. You recall that the Grunheisen diverges for a quantum continuous transition, but does not for a quantum first order transition, but it will jump sign from here to here. So we should be able to tell that. We're still working on more experiments, but also longitudinal sound should see something. We have a number of suggestions for experiments, and they're developing as we're really trying to hone in whether this is truly just a quantum critical point or a quantum tri-critical point. And that's a subject of discussion in our collaboration at the moment.
Premi, can I also ask a question on the quantum Larkin-Pikin problem? Sure. So of course, one way you can get a non-local interaction vertex is by quench disorder, at least in imaginary time. Right. So have you thought about whether this continuous transition at zero temperature is stable against
disorder?
That's
actually a very important question. That's actually one of my questions here. As you know, our alpha is greater than 0, and so we have to worry about the Paris criteria. And so one of the issues that crops up is how robust you are to disorder. And the honest truth is we haven't really studied that yet, but to make contact with real materials, that's actually very important. I agree.
Okay, thanks. I don't know if Yasha forgot to lower his hand or if he has another question.
Yashar, do you have another question? Just to continue along the lines of your question, Frank, I should also say that these systems have strong elastic anisotropy, and so it may also be that that they drive the system inhomogeneous, which also means that you have a first order transition, and so in real systems one would have to examine that quite carefully.
Yes, but then also in principle you might have a situation where you have a linear coupling to the order parameter. I mean, yes. And then of course the whole mechanism is not.
Yeah, I agree. So this is, in some sense, this was just to try and come up with a model that was a proof of principle. But disorder is a very interesting question. Yeah, I agree.
Okay, I don't see any more questions. So so we made up a few minutes. So let's all thank Premi again for a great talk and a very interactive session.
Thank you, everyone.
Okay, so I think we can restart almost on time with Claudia's talk.